Students, good afternoon.
Good afternoon.
Afternoon, sir.
Yeah, thank you. So we had seen SR latch in the previous class, right? Where we had tried to put the values here, and we had verified, what values are going to come as our outputs. So this is our representation of our SR latch. Okay, set is 1, reset is 0. Fine. So today we are going to see an application of this SR latch, okay, which is nothing but your switch debouncer. Okay. So in switch debouncer, okay, before we get into the explanation, okay, you should know what kind of circuit that we are using. And yeah, so this is nothing but a voltage supply, okay, and a switch which connects A and B. Okay. So this is my voltage, okay, across one axis I have time, and across the other axis I have um, the amplitude, the voltage levels of A. Okay, and here you can see that for B, okay, so whenever B is active, okay, so I will see that whenever A is active, B is not active because it either connects to B or it connects to, or this switch connects to A, right? So these two A and B work opposite to each other, okay, because the switch cannot be connected to both the points, right? So the switch is starting from here and then it's connecting to B. So similarly, in the next position, it can go to A. So which means whenever there is A active, okay, you can find that B is actually inactive. So you find that there is a low pulse here, okay, right? So if you can see, okay, what is happening is you can see a lot of pulses here, okay, small pulses. So this is because whenever the switch is uh, in contact, okay, there will be a sudden spike of voltage, and then it drops down, then suddenly there is a spike. Then at this point of time, okay, at this point of time, you would find that your voltage is stable. So similarly here for B also, you can see a lot of small pulses. Okay, these are actually not needed. Okay. So when we apply an SR flip-flop, okay, and SR gate, okay, so you can see that the outputs that are coming, okay, so I will give the same inputs here, VA and VB, same inputs, and you can see that the outputs are actually, much refined. You can see that it is a proper form of pulse. So students, did you all understand as to how we got these waveforms and what is the role of this latch? Was it clear? Yes. Can I proceed?
Yes, sir.
Okay. So here we are learning about this application of SR latch. Latch means it's holding on to a particular value. Okay. Okay. So it's holding on to a particular value. So common problem involving switches is the occurrence of contact bounce. So this contact bounce is because of, it as soon as there is a contact that happens, okay, there can be a bounce, a spring action. So because of the spring action, having contact and losing contact, having contact and losing contact, so you can find that these pulses will actually occur. So whenever there is a contact, you can find that these are the high pulses, and whenever there is no contact, you can find that there are no pulses. Okay, fine. So the next thing that you can see here is uh, okay, the voltage at terminal B is plus volts, okay, while the voltage at terminal A is 0. As I told you, these voltages will act opposite to each other. So the switch cannot be connected to both the points B and A at the same time. Okay, so we have A point here, okay, and I have the B point here. So this switch cannot get connected at the same time to both of the points, right? So at first position, it might be connected like this, and at the next position, okay, it could be connected in a different fashion. Okay, it could be connected here. So which means the switch, as soon as it touches a contact, there can be an occurrence of bounce. This opening and closing effect due to the springness of contacts. So every contact will have a spring, right? So because of the spring effect, what is happening? There are several pulses that actually comes. Okay, so these are those pulses that you see. Several times before the center contact and switch remains in its upper position. During contact bounce, the center contact does not return all the way to the terminal B. This occurs again when the switch is moved from the upper to lower position. This effect of contact bounce is normally undesirable. So I do not want to see this kind of pulses. Okay. So instead, I should be able to see this kind of stable pulse. So this pulse is happening because of switch bounce. Okay, so this is when I normally give a voltage and then I connect to points A and B and I calculate the voltages across A and B. Okay, so what I will do next is I will try to apply the outputs which comes here. Okay, the output from A and the output from B. So this will be directly connected to an SR latch. So if I connect this to an SR latch, what is going to happen? We are going to give the same inputs which we gave here. By the way, this VA and this VA both are the same. Okay, so we are giving the same inputs, VB, these are the same. Now the only thing that you have to concentrate is 1, 2, 3, 4. Okay, so these two are my inputs and the last two. So these two are inputs, okay, and these two are my outputs. Okay. So once I give this inputs here, what is going to happen? I will not see these kind of pulses. Okay. So these kind of pulses are not observed. Fine. So let us now see what is happening. Now I want you to carefully compare voltage A, okay, that is VA and Q. So if you see that what is happening is all these pulses are combined. Okay, so these pulses are combined, all these pulses are combined and it is made a single pulse. So what is that single pulse? It is this one. Okay, so which means these irregularities that you see are taken up by the SR latch and the values are retained. Remember why we are using a latch? A latch is a memory element, right? So as soon as the value is there for a certain amount of time, it will have something called a threshold time. Okay, so if if the bounce happens less than that time, okay, so it will not consider that value. So which means it is just like neglecting the smaller values. So these values that you see here are very minute. Okay, so let me just highlight so that you'll be able to understand. So these values that you see here, okay, are very negligible. So what it will do is it will also treat it as high. Okay, and all this full thing is considered as high value. So if you just put a dotted line, you will be able to understand. Okay, so the whole thing is taken as my high switch, high pulse. Okay, and this is about your Q, right? Now let us see the opposite, which is for your B. So in B, what is going to happen? All these irregularities that you see, okay, these irregularities that you see are all taken as high. Okay, so which means what we are trying to do here is Q is opposite to Q bar, right? So VA is also opposite to VB. So VA and VB are opposite to each other. So similarly, Q and Q bar are opposite to each other. Whenever this is 0, okay, whenever this is 0, Q is 0, I have Q bar as 1. Whenever I have Q as 1, I have Q bar as 0. Whenever I have 0 here, I'm getting 1 value here. Okay, so this is how you should be able to conclude that because of your SR latch, what is happening, we are not able to see these kind of irregularities, these kind of bounces. Instead, I am able to see normal pulses without short pulses. Is that clear, students? Any doubts here? Any doubts you want me to repeat, or is it fine? Have you all understood?
Could you repeat once more, sir?
Once again, which part you didn't understand, Rohit?
The waves being converted.
Waves being converted.
Signals.
Okay,
Yes,
fine.
sir.
So these irregularities, okay, if you can see this blue circle that I've drawn, these irregularities are treated as high value, okay, and these irregularities that you see are taken as high value here. So which means we are trying to see that if the off time is too less, then it is not going to consider it. Say for example, if you lose 1 rupee from 10,000 rupees, does it matter? Rohit, I want you to answer. If you lose 1 rupee from 10,000 rupees, does it matter?
No, sir.
No. But if you lose 9,999 rupees and save 1 rupee from 10,000, does it matter?
Yes, sir.
Yes, it matters because it's a lot of money, right? So similarly here, what is going to happen? These short pulses that you see, all the short pulses are neglected, and you can see that there is a majority of high pulses here. So that is taken into consideration. Okay, so that is taken into consideration.
Sir, so is there a difference between, like, can we differentiate whether it's a short pulse or like very high pulse?
We can differentiate. See, you can do that with the help of timing. So once you connect this circuit to an oscilloscope, okay, this is across your time only, right? So this is across your time. So you will be able to see how much duration that pulse is. Okay, so short pulses are all neglected, and those which are high are treated, and it is combined. And one more best thing about this
Are there
latch,
any values? So are there any values for short pulses?
No. There
maximum
is no
values or minimum values?
No. There's no any values. Short pulses are very meager values, very small values. So those small values are considered. Okay, is that clear?
Yes, sir.
Okay, so if we want values, then what we can do is we can actually connect this to a CRO, this circuit to a oscilloscope, and then we can generate this waveform, and we can calculate what are the timings, and accordingly, we can come up with numbers. But right now, since this is theoretical point of view, okay, the objective here is for you to understand if there are irregularities like this, if there are pulses like this, short pulses like this, using your SR latch, okay, you can actually convert them into a proper stable pulse. So that's the motive here. So I hope you all understood.
Sir, in the circuit, sir, in the top left corner, why is it earth, sir? The terminal E, why is it earth?
Top left. This one?
Yes, sir.
No, this is your negative potential, and this is your positive potential.
So not
this
the source, sir. Like the terminal E, why is it earthed?
This is the load. This is the load. Resistance is nothing but the load.
Oh, okay.
Okay, so see, if you connect two wires, how will you know if you connect the load, right? So the load is nothing but your fan, your light, your geyser, Okay, so if your light turns on, then only I will know that the current is flowing in, right? So this is the load, and we design the circuit in such a way. Okay, these are all resistance. Okay, we design the circuit in such a way that we have a load and extra current doesn't pass through this latch. Okay, so we want very minimum values to pass through latch. So that is also one of the reasons of having the resistance.
Okay, yes, sir.
Fine, fine. Okay. So what will happen? Suppose I don't have a resistance. Can I give 240 volts as an input to my small transistor, which actually needs 5 volts? Not at all, right? So I will have to use a resistor instead, a load. Okay, resistor in general called a load, and then I can downscale the voltage and then pass the values to my latch. Is that fine?
Yes, sir.
No? Okay. So we will proceed now with the next concept. So this is about your debouncer switch. Okay. So for your benefit, I have even written a lot of explanation here. Okay. So we'll just go through and try and check few points. A very simple but important application is to eliminate the effect of contact bounce. Okay. So all this that we saw here is contact bounce. Positive logic plus volts corresponds to logic 1 and the lower values to logic 0. Okay. The use of two pull-down resistors, okay, logic values are ensured at the SR terminals of the SR latch whenever the center contact of the switch is not connected. Okay, so whenever it's not connected, these terminals, these loads will actually fall on to either of the terminals A or B, that is whenever the switch is open. Hence, by the use of SR latch, the effect of contact bounce is eliminated. So the main thing that you should understand here is by using SR latch, these pulses can be nullified. Okay. Now, this is S bar R bar latch, okay, which is opposite to what we saw the SR latch. So there we used a NOR gate. The opposite of NOR, we will be using another gate, which is NAND gate for implementing S bar R bar latch. So the same concept here, we'll be using an AND gate with an inverter. So this converts to NAND and it is cross-coupled. Cross-coupled means the output of one of the gates are connected as input to the other. So the output here, Q, is given as input and the output here is given as input to the other. Okay. So when it is 0, 0, this will actually give me high values, okay, 1, 1, which means it is not needed. It's in a toggling state, just like how we saw here for high value. Also, for high value here, we got this effect. But when I put S bar, R bar, the opposite of it, at 0 only, I am getting this kind of unpredictable behavior. Okay. That means it's a toggling state. I don't need this kind of states, on off states. I do not need. I need states which are actually stable like this. Okay. Right. Another type of latch, which is S bar R bar latch, is constructed by cross coupling NAND gates. It's a bistable element. Also, we can convert it to a bistable element when we give a value 1. Okay, when S is equal to 1 and S bar is 1 and R is 1, we get a bistable element. Bistable means whatever is in the memory, the same thing is retained. Q and Q bar means whatever is there in the memory is retained. So that kind of memory I can invoke only by giving values 1 and 1. Okay. Now we will try and give some values here and understand as to what is happening. Okay. Let's say our S bar is equal to 0. Okay. And R bar is also equal to 0. Or should we take the other case, 0 and 1? We'll take 0 is S bar R bar is also 1. So anything that gets multiplied here, is going to be 0. When it comes here, it's going to be 1, right? So 1 is going to come here. So 1 into 1 is 1. I'm getting 0 here. This 0 again comes here. So 0 into 0 is 0 and 1. So what is my final value? 1 and 0, right? For 0, 1, I'm getting 1, 0. So students, you have understood now how we are trying to analyze the circuit. Yes, yesterday also we have seen this, isn't it?
Yes, sir.
Okay, fine. So the same way, okay, the same way you can actually analyze it, right? So these are going to be your symbols, okay? Your SR. So bar is used because um, we can either use a bar or these bubbles are used, as I told you yesterday. So these are some of the representations at the output side, sorry. So Q bar is here, Q bar. So whenever there is a bar, you have a bubble in front of them. Okay. Next, we will be moving into something called gated latch. Okay. So gated latch is going to have an enable. Okay. So we will use a clock signal in order to enable things. So these were the previous ones that you saw did not have um, any enabling concept. Okay. So just as per the combination of input, accordingly it was starting to work. But here now in the gated concept, we will see as to how this clock or enable signal works. Fine. So the gated SR latch. So the inputs for both SR latch and SPR latch are asynchronous or direct. So that is a very important point that you should understand. Asynchronous means it is not in sync with the clock. So it just randomly starts um, as soon as there is a combination given at the input. So it's instantaneous. That is, a change in value of inputs causes an immediate change to the output. So that is called asynchronous type of working. It is frequently desirable to prevent input activation signals from affecting the state of the latch immediately. See, we do not want, as soon as we give inputs, okay, we do not want the outputs to change. That is because some of the other circuits will be connected to this output. So as soon as the output changes, if it is not passed to the next stage, then it is going to cause a problem. So we want the outputs to remain stable for at least some proper time. So if the outputs are not stable for a proper time, then that wouldn't actually pass to the second stage. So you're understanding, no, students, what I'm trying to say? Yes? Okay, thank you for that confirmation. So your output time should be majority, so that it actually passes to the next stage of the circuit. To allow input changes to be effective only during the prescribed period of time. For these situations, a gated SR latch is used. So in such situations, to keep it stable, okay, we will be using the gated SR latch. So this is also called an SR latch with enable. So to confuse you, examiners might ask, explain SR latch with enable, or the same question can be gated SR latch. Okay? Or they can also use using clock signals, explain SR latch. So all these three can actually be the same. Okay, fine. So we will be using a NAND gate here. Okay, and the reason why we are using a NAND gate here is because what is going to happen if I am actually interested in multiplication. So if this is 0 here, which means anything that comes out here, okay, anything that is given here with R is nullified. Anything given with S is nullified if my C is equal to 0. So that's the reason I'm using a AND gate and a bubble. So NAND gate, fine. So similarly, you can actually see that whenever there is 0 for your enable signal, it means that your S and R is don't care. Why is it don't care? Because it doesn't matter whatever values you give, okay, because it is disabled. So the values that are going to stay are going to be your memory values. Okay, Q and Q bar are nothing but the previous state outputs. So you can even calculate this, okay, 1, 0, and 1. So you want me to show one of the things as to how it works?
Yes, sir.
Okay. So we will take 0 and 1. Okay. So anything that multiplies is going to be 0. So I'm going to get a 1. And here I'm going to get a 0. Okay. So which means 1 is here and 0 is here. So anything that gets multiplied here is actually 0. So I should be getting 1. And this 1 will come here. So 1, 1, 1. Then I should get 0. So are we getting those values here? Yeah. Students, are we getting those values? Yes. Understood?
Yes, sir.
Yeah. So this is how you can analyze different values and check. So the most important thing here, that you should remember is whenever your clock is 0, okay, this state is going to be the memory state, which means here clock becomes 0. So whatever S you give doesn't matter, whatever R you give doesn't matter. Okay, so ultimately it is going to have the same value, okay, which is going to be retained. So just see, for example, it is 0 here. So 0 into 0 is anything 0. So I should be getting 1 here, right? So here also I should be getting 1. So 1 will come and sit here, and 1 will come and sit here. So I do not know the values here, right? I do not know the values what are going to come here. So either it can be a 0 or a 1. So whatever values was there previously, the same thing will be retained. So it's insufficient data for it to compute. So what is going to happen? It will retain the same values which were there previously. The values are not affected in this state. Okay. Fine. So the same thing I have written here actually extensively, and explained when C is 1, then the latch is enabled. When S and R is 1 and C is 1, it is not recommended. Okay, it is not recommended because it gets into that kind of unpredictable state, which means a toggling state. I get zeros and ones, so no, it's not desirable. Okay, now this is your D latch. Okay, and gated D latch, or we can even call it as D flip flop. Okay, so all these are gated ones are all referred to as flip flops. Okay, so yeah, so D latch. So here in D Latch, we are just going to give one of the inputs, and the same thing is going to come across the output. So you can see here that the input, when input 0, output is also 0. When input is 1, output is also 1. So D is nothing but your delay circuit. So the values will pass through, and after some time you will actually get the same value which you had given for D. Okay, so which means D and Q have the same values. And as usual, we know that Q and Q bar will be opposite to each other. So 0, 1, 1, 0. Fine. You want me to show one of the values, how it comes up, or is it fine?
Not needed, sir.
Not needed. Okay. So it's the same explanation, right, for what we saw previously. Okay. So the main thing that you have to remember here is that you have a enable. Okay. You have a clock signal wherein I can control by giving 0 and 1. So if 0 is given, my D input, whatever is given, is nullified. It's not at all taken into effect because 0 is strong, right? So it gets multiplied. But then if this is enabled, then the value is dependent on D. Okay, the value is dependent on D. And I will exactly know as to what are going to be my outputs, which is just going to be passed from one point to another point. The gated D latch is gated SR latch in which a NOT gate is connected between S and R. So if you see, if you compare this diagram, okay, and if you compare this diagram, the only thing that you see here is between S and R, I'm connecting an inverter. That's it. Everything remains the same, right? So this is your gated SR latch. Always remember, this is my bistable element, and you will give your inputs to the initial stage. So in SR, I am giving 2 inputs, right? So in my D, what I'll be doing, I will be combining them with an inverter. Okay, so this part is the same, and these 2 NAND gates are also the same as in your SR. The single input D determines its next state, and the control signal determines whether the input is effective or not. So which means it is valid or not. Should I consider the value of D or not? Okay, so that's what it means, right? So next we will be actually extensively looking at something called timing considerations. Okay, so in timing considerations, what is going to be the low to high, from high to low. Okay, so we will be seeing this in our next session, okay, where we will be studying about minimum pulse width, okay, and setup and hold times. These concepts are important, okay, which will be asked frequently in your exam point of view. And conceptually also, you will have to remember all of these points because it is very essential to know the timing concepts. So we will discuss about this timing concepts in our next session. So we were to start the timing considerations, right? So in this timing considerations, what we will see here is we will look into the propagation delays, okay, and some of the important parameters that are actually used in our timing analysis. So you will be having a kind of introduction to the timing analysis in this class, and we will see in depth, okay, the timing analysis in the next class. So as of now, we will get into the introductory part of timing considerations. Can someone tell me why is timing needed? Is timing so important?
Yes, sir.
Yes, but why?
In order to get the required output.
Okay, suppose I don't have the timing, then how is it going to impact my circuit?
There'll be a delay
Timing
in
can be
getting
considered
output
for
also.
producing the delay, no, sir.
Okay. So continue, Sign.
Sir, that's what, like, for producing the delay in the output, we can give the timing, and so that we have proper spacing of the impulses at every interval of time, we may be giving the, like, we need to consider time.
Yeah. So time is very important, where at particular instant, okay, it should be able to trigger different circuits. Okay, just like how we saw clock signal, right? So there also, you know, we can actually make sure that the signals are properly propagating, and there is a sync between the input and output. The responses to inputs are not immediate, but rather occur after some appropriate time delay. So this is done with the help of clock. A convenient way of showing the terminal behavior is a flip-flop timing diagram. Okay, so this diagram will actually depict how the inputs are, how the outputs are, and how they are transiting as a function of time. So that is your timing diagram. So let us actually look into something called propagation delay for an SR latch. Okay. So initially the value will be 0, and then slowly it turns on, and it's moving from a lower value to a higher value. It's stable for some time, and then it comes down, then 0. So just assume that this is one sort of waveform, okay, just a random waveform, and R is also a random waveform. So we will take a point in S, and then we will draw a dotted line, a marking, and we will take a line from R, and we will actually draw the marker. So once this is done, we will be now looking into new definitions called rise time and fall time. Okay, rise time and fall time. So the propagation delay is the time taken for change in an input signal to produce a change in output signal. Okay. So this change that you see here from 0 to 1 is happening at this instant of time. Okay, but you can see here, okay, what is happening? It has just reached 0, but then this midpoint and this midpoint should be the same, isn't it? But there is a short delay between this point and Q point. So this is nothing but called your propagation delay from low to high. LH is low to high, PP is your propagation delay. Similarly, okay, you can also take another one here, okay, and try and check as to what is your value from high to low. Okay, so this point should be here, but then at this point, okay, it is falling. So which means this line is delayed by certain amount of time. So this time is nothing but your propagation delay from high to low. So this is called your falling edge, and this is called your rising edge. So TP is your propagation delay. So students, were you able to understand what was explained? Any doubts, please ask.
Sir, can you repeat once again?
Okay. Now the main thing that you should understand is whenever we give an input, the same thing should be propagated from the circuit, and towards my output also I will need the same thing. Okay, if I'm passing a 0, or if I'm saying high at the input side, even at the output side, at the receiver end also I should be able to hear high. Okay, if there is a mismatch, then is there a communication happening?
No.
No. So which means my input values should be passed on to my output in real time. Okay, so if there is no real time, you can just check with your normal regular operator based calls and with your IP based calls. Okay, so with your IP based calls, you can find that there is a certain time delay, right? You will be talking, and by then your friend will start responding. thinking you have stopped talking, right? So this one you can see in your internet-based calls. But with your normal calls, okay, these kind of delays will be less. Do you all agree with this?
Yes, sir.
Yeah, okay. Now let's come back to the diagram here. Now I am marking a point here, which is the midpoint. Why am I calling it a midpoint? Because it is between my rise time, okay, between the low value and the high value, okay. So how do I find that it's a low value or a high value? So this is my highest value, okay, and this is my lowest value. So I will take something which is in between, okay, in between, which is nothing but your mid state, okay, or we can call it as a metastable state. So from this point, I am taking a line. So now I am comparing S and Q only, okay, S and Q only. So keep your concentration there on S and Q. Now this lines have come here, so which means this midpoint, the rising line that I see here, should also have started here. But then is it starting there? Is it starting there?
No, sir.
No, but there is a shift. There is a small shift that has happened, right? So if I connect these two lines, is my line straight? No, right? So if in case both the dots were at the same point, then I would have got a straight line. Are you following, students? Are you following? I would have got this
Yes,
line,
sir.
right? But what has happened? The point has shifted to this point. So this difference that you see between this point and this point is nothing but your propagation delay taken from moving to a low value to a high value. Low value is 0 here.
So, sir, the propagation delay is always taken with reference to the base.
Yeah, propagation delay, you can take it at any point of time. This becomes easy for us to analyze. See, because I'm taking a slant line here, so I will know that this is my midpoint, right? And from here, I will draw a line. And here also, it should have been here, but then there is a shift here. So it's easy for me to understand because it's a slope, right? So if it's a straight line, then there's no point in comparing two straight lines, isn't it?
Yes, sir.
Yeah, because these are all train of values, train of pulses. Okay, so I can actually take this at any point of time. It's not that for the chain you should just cut at the first end or at the last end. Any link you cut, the chain is disconnected, right? So this is a chain of values. So at any point I can mark and I can take it. So this difference that you see here is actually called your propagation delay. So much of delay is there when compared to my input and output values. Understood, right?
Yes, sir.
Yeah. Okay. So the reverse happens with the falling edge. Okay. So the same thing happens with the falling edge, which is nothing but called your PPHL, moving from high to low. Okay. Moving from high to low. Okay. Now you see, yeah. So you can see the differences here also, right? So the same differences that you can actually look into. So R you can compare, and it should have been somewhere at this point, and then it shifted. Okay, and we are able to see your values which are delayed. So the same delay. So here, whatever delay we see, you can almost see the same delay with the rise and fall edge. Almost they both will be the same. Okay. The various propagation delays of flip-flop are finite slopes of rising and falling edges of signals as shown. Since their midpoints are used in specifications of delay times, the outputs do not change instantaneously to an input change. Okay, so here at this point I want high. Okay, so let me mark it. See, at this point I want high value. Okay, but I am not getting that high value at that point, right? Am I getting high value at that point? No, but it's still in what phase? It's in transition phase, right? But then I am getting that high value at this point. At this point, I'm getting the high value. So there is a shift that has happened, okay? And that is nothing but called your propagation delay. Clear, students?
Yes, sir.
Yeah. Finite slopes of rising and falling. The outputs do not change instantaneously to an input. So there is no instantaneous change. As soon as the values at S change, you cannot see the values changing here right away at Q. Nor do the outputs change simultaneously. TPHL is nothing but your propagation delay from high to low, that is from 1 to 0 in the positive logic. Similarly, TPLH, okay, from low to high. Okay, so I think probably we will see the upcoming concepts, your pulse width in the next class, but maybe we'll try and understand this concept here. Okay, right? So let us see a train of pulses. Okay, S and R. I just have a random value of those, and of course at every pulse I am drawing a line. These are pulses of S, and those lines, those dotted lines are drawn. You can see that there is a small delay here, right? There is actually a small delay here. So there is a small delay here. So that is nothing but your propagation delay. Similarly, the lower value, okay, it should have gone low at this point, but then it is going low at this point, right? Are you able to understand, students? Here, I should have got low value, but I'm not getting it there. Instead, I am getting it at a different point. I'm getting at this point. Understood? Right.
So, sir, T3 minus T2 would be the delay.
Yeah, we can consider in that way also. So I've drawn lines, right? Your dotted lines here, and yeah. So now what you can do is you can try to compare your S and R truth table. So 1 and 0. Okay, what you would get, that is actually your values. You just bring up your truth table. So when S is 0, Q is 0. When S is 1, Q is 1. When S is 1 and R is 1, then we get a toggling state. So which means the output is actually following your S, isn't it? When it is 0, it is 0. When it is 1, it is 1. Now, what you can also try doing is you can compare both the values now, S and R. Okay, when S, let's take the 0, 1 is 0, 1, 1, 0 is 1, 0. Okay, now at both high state, okay, we are getting toggling state, and at both 0 state, we will get a memory state, which means previous state is followed. Okay, so that should be kept in mind here. And you can look at these waveforms. Okay, so you have 0, 0. Okay, so 0, 1, 0. I should be able to get a 1, right? Then your 0, 1, 0. But at this point only, at this point, after some time, I'm getting the value, right? So which means it is waiting for the value of R also. R also. Then till this point, it maintains high value. Till this point, it maintains high value. As soon as it gets this value, after some time, the value changes. Students, you're understanding what I'm trying to say? Yes?
Yes, sir.
Yeah? Okay. So similarly, you can see the values here, 0, 0. Okay. So which means whatever was previous thing, the same thing will continue. Up till where? Up till this value. Up till this value. Then I have a 1 and a 1 and a 0. Okay. So I should be able to get a 1 and a 0 here. Okay. So the same thing is continued. Then I have a 1 at this point. At this point, I have 1. Okay. So what is going to happen? 1 and 1. Okay. I should be able to get a toggle state. Toggle state means what? Whatever was there previously, that becomes 0. 1 will become 0. Then it will look for the same state. Okay. After this toggle state here, after the toggle state, high value, low value. So which means I should be getting high value here. Understanding, students? Right? So this is how you should be able to mark your pulses. Okay, accordingly mark your pulses and try and check the values for your Q and Q bar. Okay, so we will stop here and we will continue this discussion in our next class.